The basic purpose of localizing variables is to prevent conflicts between variables in different parts of the system. For example, if a variable x is assigned a global value and then a program is entered that assigns a different value, in the absence of any localization, evaluation of that program changes the global value of x. This effect can be prevented by enclosing that short program in module, which localizes the variable so that evaluation of the program leaves the global value unchanged. Similar variable localization can be achieved in this example using the with function. For example, this program also assigns a local value to x and also leaves the global value of x unchanged. Although the with and module functions use similar syntax, the effect of with is more similar to application of a pure function. This input, for example, uses a pure function to do effectively the same thing as the program that used the with function. Both programs work by establishing x as the name for a value and inserting that value into a program, and both programs leave the global value of x unchanged. Comparing module with and application of a pure function, module localizes the names of variables, and the program in the body of the module is free to change the values of those variables. Pure functions and the with function instead work by inserting fixed values for variables into a program in which those values are constant and are not changed by the program. Another place where variables get localized is in rules and definitions, where the names of named patterns are localized. For example, in this input, the name x of the named pattern x blank on the left side of the rule is local to this application of the rule. The local variable here is x. Application of the rule attaches a value to that variable and inserts that value in place of the variable on the right side of the rule. This localization is done automatically. Application of the rule leaves any global value of the variable unchanged, and all of this works the same regardless of any global value of the variable. The names of named patterns are also localized in definitions. For example, this defines a function f where the argument is a named pattern. As in application of a rule, application of that definition attaches a value to the name in the named pattern and inserts that value in place of that name on the right side of the definition. And this also leaves the global value of x unchanged. One remaining way of localizing variables is using the block function rather than using module. For example, here is the earlier module example and the same input using block. Both programs give the same result and are interchangeable in this example, but block and module are actually quite different functions and are designed for different purposes. Block localizes the values of variables, while module localizes the names of variables. For example, start by introducing two global variables, y and t, and consider a short program using block and the same program using module. Block works by temporarily setting aside the global value of the variable t, evaluating the second argument of the block, returning the result, and then restoring the original value of the variable. In this example, the local value that is assigned to that variable gets used throughout the evaluation, and in particular, that local value gets used when the local variable comes up during evaluation of y, and that local value is returned in the result. Module works by inserting a new unique variable to use in place of the variable t, and then evaluating the second argument in the module. The evaluation of the second argument in module assigns a local value to that new unique variable, but this has no effect on the variable t that arises during the evaluation, so the result still uses the global value of that variable. In the Wolfram documentation, the method of localization used by block is called dynamic scoping, meaning that localization applies dynamically while the body of the block is evaluated. And the method of localization done by module is called lexical scoping, meaning that localization applies to variables that occur literally within the module. In most examples, the new unique variables that are introduced by module are only used internally and are discarded at the end of the evaluation, but those variables are seen in some situations. For example, this input shows a module that does not assign a value to the local variable, so the return value includes the unique variable that was generated within the module function. Probably the most common use of dynamic scoping, like the scoping done by the block function, is the automatic localization of the variable in functions like table and plot and similar functions that use iterator variables. The table function, for example, works by assigning values to the iteration variable and evaluating the first argument in table after each assignment. This works even if the variable is not explicitly present in the first argument of table and only comes up when that argument is evaluated. Block also provides a way of doing evaluations in the presence of a temporary redefinition of some constant or some function that comes up during that evaluation. For example, this uses block to do that same table evaluation with an alternate definition of the built-in cosine function. Both of these examples depend on localizing the variable without changing the name of the variable. All of the other variable localization functions other than block, including module and with and rules and definitions and so on, use lexical scoping, which localizes the names of variables. Lexical scoping is especially important when scoping constructs are nested within other scoping constructs, which is quite common in realistic programs. For example, here is a definition that includes a module where the name of a named pattern is localized as part of the definition, and the module is separately used to set up a local variable on the right side of that definition. And here's a typical application of that definition where the argument of f is inserted into the module and the module then evaluates to the intended result. The argument of f is inserted in place of x and the value assigned to the local variable in module is inserted in place of n. There is a potential conflict if the argument of f happens to have the same name as the local variable in module, but since that name is localized to the module, the evaluation continues to work as intended. This does not work, however, if the same definition is written using block. If the argument of f is not the same as the local variable in block, then the definition works as before, but there is an awkward special case if the argument of f is the same as the local variable in block, since the two variables will then be treated as the same variable, and the value that is assigned within the block gets used as the value for both variables. The automatic renaming to localize variables happens for any nested combination of structures that implement lexical scoping. For example, this input shows a function-valued function where a function is returned when the outer function is applied to arguments. The result is the inner function with values inserted for the variables from the outer function, and the variable of the inner function is renamed. Renaming of that variable is done to prevent a conflict if the arguments of the outer function use a variable with the same name as the variable in the inner function. A basic simple fact about any variable localization is that it can only be done if the variables to be localized are held unevaluated until after they've been localized. For example, here's a typical use of module except for evaluate enclosing the second argument, which results in a global value being returned rather than the local value that is assigned within the module. Evaluate causes the argument of module to be evaluated before module ever sees it, and so the global value of the variable gets used before the enclosing module has an opportunity to do anything about it. The arguments in module are normally held unevaluated because module has the hold all attribute. Almost all scoping constructs have some way of holding arguments unevaluated. For example, the function also has the hold all attribute. The names of named patterns in rules and definitions are held unevaluated because pattern, which is the function that is used to give names to named patterns, has the hold first attribute. The only scoping constructs that do not hold arguments unevaluated are the set and tag set functions, which give immediate assignments, and rule, which gives immediate rules. For example, application of the immediate rule in this evaluation simply uses the global value of x, since the right side of the rule is evaluated before anything can be done to localize x. Immediate rules and assignments are nevertheless treated as scoping constructs, and the names of named patterns are localized if the immediate rule or immediate assignment is held unevaluated in some other way. For example, the named pattern is localized by renaming in this rule-valued function, and the rule works as intended, even though the name x does still have a global value, because the entire rule is held unevaluated by the enclosing function expression. One other lexical scoping construct is dynamic module, which is used in examples like this one to localize variables in dynamic output. Moving the slider in this result changes the value of a variable t, and dynamic module localizes that variable so that moving the slider does not change the global value of the variable. The key difference between dynamic module and module is that dynamic module localizes variables in dynamic output, while module localizes variables during evaluation. In a typical module program like this one, the values of local variables are changed using assignments, and in a comparable program using dynamic module, values of local variables are changed using interactive controls like sliders in the output. As can be seen using input form, the result from dynamic module is actually the displayed form of a dynamic module expression. Module has no comparable effect on output, and output from module does not retain any consequence of having come from a module, but the dynamic module expression returned by dynamic module is part of the system in the notebook interface for localizing variables and dynamic output. Dynamic module is used automatically by functions like manipulate. This result from manipulate, for example, returns an output that uses a variable that is localized to that output. Except for formatting, a comparable result with a localized variable can be obtained using dynamic module, dynamically updated variables, and a control. That's the end of the examples. Additional information on all of the functions that came up in this section can be found in the Wolfram documentation by following links to individual functions from the guide page on scoping constructs. Another good source for information on all of these functions, other than dynamic module, is this tech note on modularity and the naming of things. Information on dynamic module, which serves a qualitatively different purpose, can be found in the tech note Introduction to Dynamic, particularly in the section on localizing variables and dynamic output, and in the sections on dynamic module in the tech note on advanced dynamic functionality.